Sorry, can we use this device for the rest of the presentation? Okay, thank you. Perfect. So thank you so much for being here. And today, here in this space session, we will talk about the digital twins. And the first speaker will be Salvador. So, what's yours, Salvador?
So, thank you very much. Hello, my name is Salvador, and I'm going to present you a paper that is written by the project of COGITO. That in this case, the name is represented digital twins and their information resources with Web of Things. This is made in the heterogeneous group of the Universidad Politécnica de Madrid, and we are the ones that made this work. So first of all, what are the digital twins? I know this is about digital twins. We already know what they are, the digital twins, but I'm going to make like a little explanation. So digital twins are digital representation of a physical entity. In this case, we have two flows that goes from the physical entity to the virtual entity, and then to the from the virtual entity to the physical entity. So this is bidirectional information flow. As we know, there are a lot of information in the physical assets that, for example, can be BIM models, schedule data, information about the workers that are working in the construction site, for example, or equipment. So what we made in the COGITO project, that in this case is COGITO acronym is Construction Phase Digital Twin Model, is generating a digital twin for a construction phase, as the name says. So we are here. We have the project partners that we are here in the Universidad Politécnica de Madrid, and we have 4 pilot sites. In this case, we have here 3 pilot sites. There are one in Austria, Denmark, and Spain, but also they added a new one in Munich. So here we can see the general architecture of the COGITO project, where we can see here, and this site, the as-planned data, in this case is the physical part, but we have satellite images, 3D scanning, the geometry, and all of the information that can be captured from the physical statement. Secondly, we are going to have a data reprocessing about all of this information to get it inside the construction phase digital twin platform. That it is going to be the gate to go into the digital counterpart. And then once the information is in the digital twin platform, a number of processes are going to be processed in order to create the link data, in order to be used by the different applications that the digital twin provides. That in this case are the health and safety, quality control, adaptive workflow management, and the UI and support apps. And also all of this information that are in link data are going to be based on open standards that in the case, for example, the W3C, the semantic web of all RGF Sparkle, and ontologies like Saref, Bot, Brick, and also the Web of Things approach. So what we made in the COGITO's project is not a simple digital twin, because we are using semantics. So we are calling, instead of only traditional, like a traditional digital twin, we are calling the semantic digital twin. In this case, what it provides, we have, for example, here a table that explains. We have 5 layers that every digital twin contains, that are the services layer, data layer, physical entity and the virtual entity layers, and the connection between them. But also in the semantic digital twin, that in the traditional digital twin we don't have, we have the semantic interoperability, the discovery layer, and a provenance layer that I'm going to be explaining later. So first of all, in the semantic digital twin, we have a lot of information that we said earlier. But this information is in heterogeneous, it's heterogeneous data. It means that there are a lot of formats of files. For example, we have a relational database for the project data, a key value database for the IFC data, that are the BIM models, and a time series database for the IoT data, that are the information extracted from the sensor, and also all the services, extraction and transformation services, and data management. So what we made in the COGITO project is harmonize all of that heterogeneous information in homogeneous data that are semantically linked. In this case, it's RDF. And this is all of this information is stored in a triple store database. So next, I'm going to explain about what semantic interoperability is made in this digital twin. First of all, as we said earlier, we have 5 dimensions in the digital twin that are services, data, virtual and physical entity, and the connections. And we made a semantic model, in this case an ontology, that unifies all the information about the different layers. Secondly, as we said in the last slide, we are going to make a data harmonization, having the heterogeneous data and translating it to the homogeneous data. In this case, it's RDF. Also, we made like data enrichment where all the information is linked. And finally, we have the provenance. That is the part of the provenance and discovery layer. That is the principal part of this article. So, in the provenance part, we are going to have a lot of information that are in heterogeneous data and homogeneous data. But once we have the homogeneous data, where the heterogeneous data is going to be, we can forget about it or something like that. But for example, you have a service that requires information in raw data, like an IFC file that needs it for a specific task. But you have all the information in heterogeneous data, but where is the information, the heterogeneous file? So the approach that we made is using thin description web of things in order to unify the links of the homogeneous data in RDF that are in the knowledge graph, and also the links to the heterogeneous data. So first of all, in order to know what are the elements that we are going to represent as thin descriptions, we have here all the COGITO ontologies that are in this case facility, resources, process, quality, safety, and IoT ontology that you can look at them at this QR code. And we are going to look at what are the principal components or classes of the ontologies that can be represented as a digital twin on its own. So we have the whole digital twin of the COGITO project, but also there are a lot of information that can be represented also as a digital twin. For example, an entire project. I mean, for example, you have the project of COGITO and you have several projects inside of it. For example, the construction of a specific building, but you have, for example, four or five buildings. So one of each building are going to be a project in specific. So that project is going to be a digital. So from those ontologies, we take into account that the information that can be represented as a specific digital twin can be the facility project and the facility element, and can be represented as this way. The digital twin, the facility project, and the facility element are subclasses of platform digital twin. So to make this kind of extension to make these ontologies be unified with the thin descriptions ontology, we made an extension that is called the COGITO platform ontology. That is going to be the extension that links the part of the COGITO ontologies that are here and here with the thin description ontology that are the TD thing, HTTL link, and XTTL form, in order to provide for every digital twin a thin description and unify all the information about the respective subclasses. So as we said earlier, we are going to unify the part of the homogeneous data and the heterogeneous data in one file only. So this also make appear a new layer that in this case is this discovery. For example, you are a client of the digital twin platform and you want, for example, an FC format file that are from a specific project that contains X workers. So you can make a query with a discovery query inside the WOT type. That the WOT type is a thin description directory that we develop in order to store this kind of thin descriptions. And the semantic digital twin components will take the theme description with the information of RDF, in this case, for example, if you search for the 5 workers, and also the IFC file in raw data. So in conclusions, digital twins, that as we know, have a lot of data that has to be handled. The development of a semantic digital twin allows that all of this management of the data being semantically interpretable. And in order to not lose this heterogeneous data when we translate it to the multi-modal data, we use the word-based backbone approach with theme descriptions in order to maintain the provenance belonging to the other data defined by the digital twin. And also, thanks to this word-based backbone layer given by the theme description, we can perform the discovery part in order to obtain all the information concerning a particular digital twin in a more straightforward way. That's it. Thank you very much. Do you have any questions?
Is there any question or I do one. I will make one question. Do you have any perspective to introduce the physics-based or physics-informed modules into the overall digital twin? I mean, for example, the thermal loads and all this stuff also to have integrated in the semantic structure, or is it not the code, specific code?
To introduce the physics part.
Yeah, physics-proof, physics-informed part of the digital twin. For example, for the specific, I'm working in the thermal loads, for example, and this kind of systems to manage it into the overall system.
Okay, so the semantic digital twin, it means that you add the semantic part to all the information that is inside the digital twin. So for every kind of digital twin can be implemented the semantic. Because for it means that all the information that you have in a heterogeneous form, for example, you have one thermal information in JSON and another one in XML. But it means, for example, you have 4 sensors with those kind of information, but they cannot interoperate between them because they are not listening between them. So if you gave them like a simple way to make it interoperable,
Okay.
I have ontology. So.
Yeah, you have answers, so thank you so much. Thank you. So, Julia, going to yours now. So.
Do we need to assist you to changing the slide?
If you don't need
Yes,
this, then it's easier.
Both follow you. Okay.
Okay, hello everyone, I'm Julia and I'm working within the HESTIA project and at the Munster Technological University in Cork, Ireland. I'm a psychologist and a social behavioral scientist, and why I'm stressing this, because I will present a digital twin concept from a residential demand response from a psychological perspective. So therefore, a behavior digital twin for residential demand response, modeling intention and motivation to improve the prediction of the likelihood of reaction to behavioral triggers. So this work has been developed in the HESTIA project and which aim to enable tapping into the demand flexibility available in residential households. In using a user engagement and behavioral change for demand response represents unsolved social, unsolved challenge with potentially enormous environmental impact. So in particularly, sorry, I read the first slides and it's getting better, sorry for that. So the HESTIA project is developing a cost-effective solution for the next generation demand-side response services. And it aims to leverage consumer engagement, energy and non-energy services while engaging with residential consumers who present an untapped sector. And the key will be to encourage residential consumers to engage in flexibility, sharing and with balancing. So, enabling consumers to participate in the energy market is high up on the EU agenda. And residential demand response that is asking people to shift their consumption according to real-time market needs is one building block on this path. Looking at the idea of residential demand response to improve the energy behavior of end users, it is important to take them into account and provide them with the necessary information and triggers so that they can adapt and show the desired behavior, such as behavior should support the reduction or shifting of energy, particularly during peak periods. Up until now, financial incentives, as we know, for individuals or households showed limited outcomes. Therefore, other approaches need to be considered and tested. And the EU Commission foresees independent aggregators as a potential way forward. These aggregators rely on the modeling and influencing of actual energy behavior of participants. So, however, behavioral change crucially depends on the motivation and intention of participants, and therefore a digital twin concept useful for residential demand response not only needs to understand the technical dimension of the problem, but also the psychological dimension that drive the decision-making processes of individuals. So, to visualize the different aspects of digital twins, we will start with a general energy distribution. There is the energy production, which provides households with energy that is used for various appliances. And as before, already mentioned in the presentation before, this process can be mirrored in a digital twin, which consists of three major components: a physical object, a corresponding virtual object, and a continuous bidirectional data stream for transferring data from the user to the system and feedback from the system back to the user. So through this continuous data stream, the digital twin continuously influences and optimizes its internal representation. But now in reality, the households are not only the appliances in isolation, but they contain individuals who are using the energy by using the appliances when they want to. And this behavior is typically only considered in a very technical and abstract way, without taking the psychological variables into account. So therefore, the behavioral digital twin we have been developing in the HESTIA project is doing exactly that. It tries to assess and model the behavior of the individual actors by using well-established and empirically proven psychological behavioral models. We use these models to improve the estimation and optimization of the system. From a psychological perspective, for us, the most relevant variables are motivation and intention, which play a major role when it comes to human behavior. As mentioned before, the behavior digital twin presented here is based on behavioral theories coming from the area of psychology and social behavior science or social science. And by using those theories, it is possible to understand the single individual and their needs better and address them with a personalized message at the right time. The key contribution of this model is their proven ability to measure behavior-relevant variables by means of specifically designed inventories and questionnaires. So I'm not making something up, it's already there since decades, actually. The first model I want to present is called the theory of planned behavior. It is used to quantify intention, which is defined as the condition shortly before showing a behavior, or it can also be defined as the subjective probability of a person to perform the behavior in question in respect to a given object. And it assesses intentions through measuring so-called beliefs in a structured way. Here are some example questions from the theory of planned behavior inventory adapted to energy flexibility. For instance, the so-called behavioral beliefs are assessed using phrases like, can you It is important to me to adjust my behavior according to energy availability to support a more environmentally friendly lifestyle. Normative beliefs is phrase like most of my friends would adjust their behavior according to the availability of energy, and control beliefs is it sounds easy to use energy at the right time. And participants can answer those questions on a 5-point Likert scale, indicating if they agree or disagree. The results from these questions are then aggregated into explainable intermediate variables, attitude, subjective norms, and perceived behavioral control. And attitudes toward the behavior describes if someone holds a positive or negative attitude toward the subject, as for example, energy saving. Subjective norms explain if a person is influenced through important others or groups, and perceived behavioral control describes if a person feels able to execute relevant behavior. These are then further aggregated to calculate intention. So for those who are into math, this is how some of the formulas behind look like. So the whole model is operationalizable, and the model parameters or weights are continuously adapted depending how people behave. Another benefit of this type of digital twin is its ability to determine psychological meaning from intermediate variables. In this case, the 3 variables can be used to distinguish 8 different types of participants, and any messaging can be adapted according to their profile. For example, to design demand response messages for someone with a positive attitude towards saving energy, useful information should be provided to keep the positive attitude live. For people who are strongly normative oriented, it should be considered what others do or would do or wouldn't do. So they are very sensible to the social environment. And the perceived behavioral control demonstrates if someone feels capable to execute behavior. For people with low perceived behavioral control, messages should give very precise action plans to empower this person to act. And by assessing those variables, the different combinations of these variables, you can see on the right side, left side. Anyway, so by assessing those variables, the different combinations of these variables, positive or negative oriented, helps to create personas which have different needs in their communication. So the next theory I would like to introduce is the self-determination theory. It proposes the so-called relative autonomy index, together with a method for measuring and calculating it to assess motivation. Motivation, and contrary to intention, is the more general tendency towards a specific subject. And to explain what that means, we can think of a person who has a general positive perception towards saving energy. That doesn't mean that this person is also acting accordingly, but this person would be more likely to do so than someone who has no interest whatsoever in this topic. So the relative autonomy or motivation describes a continuum from extrinsically to intrinsically motivated people. And that means that someone who is extrinsically motivated needs strong external incentives like financial incentives and support to show a desired behavior, and normally only shows this behavior as long as the incentives are given. While someone who is intrinsically motivated acts because they like to or enjoy the behavior itself or the activity. This continuum is mapped onto certain types of regulation, which can be used to develop suitable inventories and questionnaires to measure motivation. The structure of the model is similar to the structure of the previous model. And here, goal aspirations are collected through structured questionnaires which are assessed using phrases like, for example, on the one continuum side, we have the intrinsic goal aspirations. I simply enjoy supporting the environment, even if that means I have to adapt my behavior. And on the other side of the continuum, we have external or questions which are assessing the external goal aspirations. It helps my image in the neighborhood and community to show energy flexibility. Here the same approach is provided as with the theory of planned behavior. A 5-point Likert scale is provided to the participants and they can say how much they agree or disagree. The questions are then aggregated into explainable intermediate variables again and further aggregated into an indicator for motivation. Here also the math in the background to operationalize the model is very similar to the previous model. Again, the weights are continuously adapted, improving the calculation of the relative autonomy index for each participant within the digital twin. Now it is possible to combine the motivation and intention into one concept, which gives us the predicted likelihood that a specific person will act, for example, in response to demand response triggers sent to them. And of course, the actual behavior might be different to this prediction. If we observe the behavior of a subset of participants over time, we can use the contradiction to continuously improve the models. So this systematic difference between actual behavior and intentions is a well-known quantity called the intention-action gap. And the digital twin can compare its predictions with the observed actual behavior and can be used to quantify this variable. It can also continuously update the model weights to better represent the specific circumstances of the reference group. And ultimately, the behavior digital twin can be used to predict the likelihood of each individual to act on a trigger, which is a useful piece of information to optimize who to target and when. We can also use the intermediate variables to shape the messaging, as described before in the context with the personas. And in summary, so model predictive control is challenging in residential settings where people are at the center of energy and need to be included with their motivations and intentions into the calculation. That leads to a requirement to predict the probability that a person will respond to a trigger, message taking the energy flexibility into account to ensure that the right person at the right time is addressed. And assessing intention and motivation and continuously adapting to actual observed behavior is a promising approach. And psychological inventories provide a validated methodology for measuring key variables and can be operationalized into a behavior digital twin model. So thank you for your attention.
Any question or?
I have a comment more than a question. Okay, so my name is Noemi Jiménez, I work for CEMOSA, and we have experience in two similar projects. One of them was the teacher project. It was a Horizon 2020 project already finished in 21, and it was about ICT tools to raise end user awareness. So in there we check how bad behavior affects a lot energy efficiency. And so we did gamification techniques, and now we are also working on the Balance Plus project, which is on energy flexibility and demand response. And in there, we also have a team of social scientists, and they did a preliminary study similar to what you have shown with mathematical models based on neural network to see the different motivation. And we are using that as in the initial stage of the project to set the requirements and then do the technical development so that we can raise user awareness regarding energy flexibility and demand response. And that's very interesting for everything.
Yeah, it's a little bit different because this is not about awareness as such, because awareness comes before people are already engaged. So you have the external engagement basically, where you need to find participants, and then as soon as they are engaged, you start with the theories and modeling. And this is a little bit different, but it's both very important to raise awareness, to get participants. It's a huge issue. I agree. So, like I said, it's a little bit.
It's a little bit different. And in our project, we have pilots in the residential sector, and those are the most difficult to raise awareness. And then on the industrial sector, that's quite easy. But for the residential sector, we also are developing mobile app applications so that they see the benefit on energy flexibility.
The front end, how you communicate with the people, like through a mobile app, is extremely important. So it needs to be really adjusted to the different personas you have in the project. And it needs to address all the different needs. So you can't just go and do whatever you always did or so. So really think, and it is possible to match the different theoretical aspects of the personas to a front-end user experience design. So, but it's tricky and it takes a lot of work. So, yeah.
It's just a curiosity because I'm not sure if you already demonstrated or tried this in a practical case. And in the case you did, I wanted to know if you had the time to observe the behavior and compare with the predictions made, and how was this?
Yeah, that's the thing. The evaluation phase is running. The good thing is the theories themselves are all well validated. So I don't have any doubt that they are not measuring what they are supposed to measure. So they are around since decades, since the 60s, 70s. So they are tested in many different areas, also in energy. And I don't doubt that there are any issues with that. Behaviour Digital Twin, how it is presented here, it isn't tested yet, so we don't have data yet. It's just a theoretical approach we like to try out as another idea how to approach the energy flexibility and all the issues around it. But what we did is parts of this Behaviour Digital Twin was tested in the health sector. A little bit different, the layout. I worked with much more theories, and there we got very positive results. People actually changed their behavior and their attitude in a positive way. So that was very promising, and I hope that we can achieve the same in the energy sector here.
Second question? I do have one. Maybe for both. I was wondering, for example, energy communities. I guess that HESTIA is related to the energy communities, and where the engagement plays a huge role. And I was thinking about different segmentations on the engagement residential sector, like for example, with different income, different educational levels. And which do you think are the main barriers to have an overall model, the twin, for all these stratifications? Are the parameters the same, or because the intentional motivation could be completely different?
They can be completely different, yeah.
And maybe can be run by completely different parameters. So.
That's true. The thing is, what the Behaviour Digital Twin doesn't do, because it doesn't need to, is assess demographics. So we really just assess the psychological variables, motivation and intention, and really address only this. It's independent if somebody it has a high social status or a lot of money or little money, or it doesn't matter. The motivation is you can assess the motivation and profile the people independently. I know it's very common to try to mix this up, but the theories themselves don't need to. What you can do is, what is definitely an interesting thing to do is, you can assess the demographics separately and then compare it with the results from the motivation and intention you got, and then see if you can cluster the people in this regard. But it's not necessary for phrasing the messages or so, the trigger messages or push notifications or so on. So this is independently.
And do you think it could be decoupled, the cultural parameters? For example, in the north part of Europe and in Spain, we don't have the same cultural values programmed in our brain. So
no, but this is also an external aspect again. It's like I said, you can assess this and then compare it with what you got through the questionnaires. And make nice statistical analysis out of it and really come to more conclusions or more results. This is definitely a good thing to do. I don't deny that, but it's not necessary to calibrate the behavior digital twin as such.
yeah, that's one. And are you planning to set a database, a specific database, for example, a specific European region or something like this, to be enriched during the projects within different project developments, to have these models for the rest of the people, for using these data sets for training this kind of models, behavioral digital twins?
Yeah, the digital twin in the HESTIA project is designed as a service for the model predictive control, so it can be requested and the questionnaires can be sent to the participants through a front-end medium, and so of course it would be interesting definitely to broaden the applicability or the application of this in other projects. So I don't know if this was the
I was more referring to making public these data sets within the DRDR, the DRD, or I don't know, the protection policies. But to have these data sets, these behavioral data sets for the people to train their own specific digital twins, behavioral digital twins. Like for example, you can download that data set regarding the I don't know what in Spain, but the same for the behavioral, to train behavioral models, for example.
I don't really understand what you mean. Sorry.
No, I was trying to ask if you are planning to share this information, this practical validation information, and to set that database to share with other people. To have enough information to for example, project in Finland could also feed this data set and have more information to be more effective information models.
I guess you could do that, but it's not in the pipeline yet. So, yeah, probably you could do that.
I think it would be really interesting to
yes, definitely.
making models.
Yes, of course.
Okay. Any question?
Okay, just to comment, in our case, for the Occupant Plus project, we didn't did a digital twin of the behavior of the user, but we did this social preliminary study. And in our case, we consider the different geographical areas, the different cultural level, education level, and our intention, we could see who was already motivated, and our intention was to motivate those that were not motivated for the moment.
Yeah. Okay.
It's a very important
And
point.
we have nice reports on that.
Okay. Okay, thanks so much.
Okay, thanks.
So, next. It's you, Noemi.
At least just in case. And this is, okay. So good morning, everyone. My name is Noemi Jiménez. I work for CEMOSA, which is a Spanish engineering company. And I'm going to present here our developments regarding digital twin for continuous and accurate energy audits. What I'm going to present here is the result of of a research project done only internally in CEMOSA with the funding of the Spanish national government. And now we have reached a nice tool, which I will be showing you. And we are going to further develop these tools in 2 Horizon Europe projects, which are Rail4Earth and INHERIT. Rail4Earth on railway stations and INHERIT on cultural heritage. Okay, so this is the content of my presentation. I will present the context and gaps regarding energy digital twins, the solution that we provide and the use case we have and conclusions. So firstly, I would like to go a little bit into the context. So the European context is that we need to reduce energy consumption due to climate change, to high energy prices, and to energy dependence that we have in Europe. Secondly, buildings consume around 40% of energy, and that's a lot, and are responsible of around 1/3 of CO2 emission. Thirdly, 70% of building stock in Europe are not energy efficient. And due to this, there are a number of initiatives to promote energy efficiency, such as the Repower Europe Plan, European Green Deal, Renovation Wave, Fit for 55, etc. In the Spanish context, around 51% of the buildings are older than 40 years, and they are not energy efficient. And so we also have in Spain many initiatives for promoting building refurbishment. And on the other side, we are immersed in huge digitalization trends that provide nice tools to improve. We also have the electronic technology have developed a lot, and we have many sensors and IoT technology. And as a consequence, we have a lot of data which we can make use of for a better energy performance. And so in here, I'm going to present what is the needs and gap that we identify and that were the starting point for our project. Firstly, there is a large gap between the energy estimation and the real energy performance. This is called the energy gap, energy performance gap, sorry. The reason for this is, when we do the estimation, for example, when we do an energy audit, there are lots of uncertainties, and as a consequence, the estimations are very different to the real performance. That means that when we analyze the need for refurbishing, because the estimations are uncertain, there is a high risk in the investment, and so the customer don't trust the solution, and so they don't do the investment to refurbish the building. On the other hand, we also have experience, as I mentioned before, for your project, we also have experience in other projects that user behavior can make a very big difference. And we have, from the literature and from our experience, we have assessed that we can reduce around 30% of energy consumption, that people have a very inefficient behavior very frequently because they have lack of information and knowledge on energy issues. On the other side, focusing on energy expert and facility manager, on building operational maintenance, we also have estimated that around between 20 and 30% of the building operation costs are related to energy. If we consider the whole life cycle of the building operation costs are around 75%, so the design and construction cost is really small. And also, it is very difficult to identify energy inefficiency and malfunctioning during the operation of the building. So this is the problem we are tackling. And for this, we propose to do energy refurbishing of buildings based on what we call continuous and advanced energy audits. And for that, we use a digital twin that we have developed in CEMOSA. So when we're going to tackle an energy refurbishing, first we need to do the energy audit, the initial energy audit. So we propose the initial energy audit, which is the conventional one, in which we visit the building, we take data, we do models and simulation, and so that is the same conventional energy audit. In our case, in CEMOSA, we do that with our digital twin tool, so that we have a higher level of automation. And as I will show you, the energy models that we achieve are very accurately because they are calibrated very precisely with real-time monitoring. Then, when we go to the customer, we do the energy audit, the initial energy audit, but when we leave, we leave the customer with our tool, with our digital twin tool. And so this is what we call intermediate or continuous energy audit, because the tool is there and it assesses the performance of the building continuously. So the advantage of this tool for the facility manager and the building user of the building in which we are in our customer, they have a fully automatic tool, and they can improve the performance of the building, and they also can identify some inefficiencies. And then finally, in many buildings, you have the initial audit where you get your label, and then you need, after a while, you need to do a renovation audit. So the third step is the renovated energy audit. That can be because you need to do that, or because in the building there has been identified some kind of inefficient, and they want to do a new comprehensive energy audit. In this case, when we visit again our customer, the process is done very quickly because we already have the tool and we have been getting a lot of information. And so, well, this is done very quickly, and we can do a very deep analysis because we have a lot of information. As Salvador, I'm going to in the initial presentation, I'm going to explain a little bit what a digital twin is, or what is in our concept, because people always use the word digital twin, and I would like to focus a little bit. So our digital twin is a virtual replica of a building, in our case, a building. And in our case, the digital twin includes the static data, which are the big models of everything that we have, the dynamic data, in our case, the real-time monitoring data. We also have indicators, which we achieve after some pre-processing of the data that we have. And we also have, in this digital twin, we have the possibility of doing a scenario simulation, so that we can run what-if analysis and use and develop energy performance model. So on the top, you can see what is our digital twin. And here I wanted to focus on the definition. This is the definition given by Autodesk in relation to digital twin with the different levels. So I just want to see the parallel line between the definition by Autodesk and the CEMOSA digital twin. So level 1 is the descriptive twin, which is, the 3D model, let's say, or the BIM model. The level 2 is the informative twin, where we have another layer of operational and sensory data. In our case, we integrated there. The real-time monitoring data. The level 3 is the predictive twin, where we have another layer of processing to gain insights. In our case, in the level 3, it is where we develop energy and comfort score, which I will present late, following an energy alarm. And the level 4 is the comprehensive twin that allows simulation of a scenario and what-if analysis. And we also have reached this level. And at the level 5 is the autonomous twins. So I'm going to present here our development until level 4. But we already have some developments on the autonomous twin. So if first here I will show some of the, I will present the functionality of our digital twin with some visualization of what we get. So what you see here is our office building in our headquarters in Malaga, where we have implemented this digital twin. So that we have a close control of the thing, and we can show everyone, no problem with confidential data. So with our digital twin, we can visualize real-time and historical data. And so somehow this is also allow remote inspection and data visualization. In here you can see the BIM model of our, this is the second floor in particular. And I have written this because I could see yesterday that the quality was not very good. So in here you can see this is a sensor that is related to this fan coil. And so when you click here in the digital twin, you can see the performance of the sensor in particular. In here, we have on the rooftop, we have a chiller. And so when you click in here, you can see all the energy performance and the static data of that chiller. We also, with our digital twin, we also can produce heat maps of energy and indoor environment condition. For example, in here, you can see the heat map of the temperature, and we have defined the boundaries. So if we are blue or red, we are out of comfort. In this case, we are not out of comfort. Here you can see the energy consumed by the lighting system. And you can see, again, we have defined a boundary. Obviously, we are, in the case of temperature, we need to be in between the boundaries. For lighting, if we don't consume any energy, that's good. And as you can see here, in the ground floor, the lighting behavior is not efficient. So people is consuming more than expected for the condition on this particular day, with the lighting, with the lighting coming from the windows and everything. And here you can see a heat map of the CO2 levels. Again, we have the boundaries. Again, if the CO2 level is too low, it doesn't matter. Maybe there is no one there, but we shouldn't reach over the red path. We also have included in our digital twin some kind, what we call energy alarms, and those are alarms that we trigger when we see a bad energy behavior. For example, in here we can see that somebody has. We have a schedule with a timetable, and when it's the time of leaving the office or a little bit later, everything is off, but sometimes people stay longer, and so they turn everything on, and then they forget to turn things off. And now we identify it, we got an alarm, and so now people behave better. This is a little bit a user raise awareness. So this is something that was very useful for us from the very beginning. Also, for example, here, this is a fan coil, and we identified that we didn't need to have the fan coil on because we already were in comfort condition. So this was also an energy alarm because we identified that we could turn this fan coil off and we still would be in comfort condition. And that is something that we are implementing, that we are running now, and so we are saving energy. Also in our digital twin, we compute what we call dynamic energy scores. With this score, I will go later into it, but with this score, we compare of our building with the reference buildings so that we can see the room for improvement. So this is a nice tool for the facility manager to see that there is room for improvement if we run the building in a more efficient way. So I have shown the functionalities and several screenshots. So what's behind this digital twin? Firstly, we have real-time monitoring. Here you can see the monitoring that we have at building levels. We measure the total energy consumption and the consumption for the cooling system, the heating, the ventilation, the lighting, and other equipment. We also measure outdoor environmental conditions to understand the behavior of the building and what we need to expect. So we monitor the temperature, the humidity, the CO2, and the solar radiation. Then at floor or room level, we measure the total energy consumption, the HV system, the illumination, the lighting, and some other equipment. And we also measure the temperature, the humidity, and the CO2 And then in relation to the envelope, we measure the temperature just outside, and I mean the temperature inside and outside. And so we have all these real-time monitoring that, well, for this we have sensor that through module send the information to a gateway, and then we have an MQTT broker that send the, well, that get the information and upload in our digital twin. So we have behind our digital twin, we have the real-time monitoring. We also have energy models very accurately calibrated with real-time monitoring. So here we have developed a calibration tool to calibrate the parameters for the energy plus model. Because we have very good parameters because they are real time. The calibration is very precise. In here you can see, for example, the real behavior of this is the cooling consumption, the real behavior. This is the behavior simulated with our calibrated model, and this is the behavior simulated but without our recalibration of the model. So as you can see here, the real behavior of the system is very similar, the blue one, to the green one. And so because our model, the calibration is very precise, the simulation are very similar to the real, and so the energy performance gap is reduced and our estimation are very precise. So for this calibration of the model, what we do? Firstly, in the initial audit, we already have an initial calibration of the model. Then, when we leave our digital twin tool in the building, in our case, we have this digital twin in our building in CEMOSA. We are continuously monitoring the system, and so every 2 weeks we do a new calibration of the system. So we do it every 2 weeks, or if we detect some kind of alarm, or if we detect that the system is not working properly, we do a recalibration. We don't calibrate all the parameters, but only those that are related to the equipment use or the degradation. For example, the use factor for lighting and other equipment, the set point, the schedule, the infiltration, etc. And this calibration is that using mathematical model with sensitivity analysis and optimization techniques. I mentioned before about the dynamic scores. So, well, we have our building very nicely calibrated because we do it very often. And in addition to that, we define what we call the reference building. The reference building is a building which the same calibration of our building because it is the same building, but the reference building is used, operated, and maintained under perfect condition. This means that the set points in the reference buildings are the set point that we can find in the regulation. If we are in summertime, we don't put the set time at 20, but maybe at 25, if that's what the regulations say. We assume that in the reference building, all the equipment is in very good maintained condition, and so the COP is the nominal value. And the infiltration, we assume a very small infiltration value. So the reference building, as I said, is our building, but perfectly operated and maintained. And so the comparison between the reference buildings and the real building that we have is, it provides a lot of insight, and furthermore, it is totally achievable to reach the values in the reference building because it is the same building. The only thing that we need to do to get close to the reference building is to operate the building in better condition. So, So what we do, we do the comparison between our building and the reference building, And with that comparison, we analyze the consumption of the reference building, which is the green one, and our real building, which is the black one. And then we define the dynamic score that I mentioned before. For example, here we define the dynamic score for the whole building per floor and per equipment. So in here we can see the dynamic score of the building is 97, so we're close to 100%. That should be the goal, and that means that we are operating the building properly. And you also can see the score that we have achieved for the ventilation, the lighting, the heating and cooling, and the other equipment. Our digital twin also propose different energy conservation measures, which we simulate using the energy boost model and the very precise calibration of the building. And so we can analyze different energy conservation measures and compare, for example, in relation to energy saving. So this is also a nice decision support system to define what we want to do to save energy. And finally, I just wanted to explain where we have tested this. We have tested this, as I mentioned, in our own office buildings in Malaga headquarters, which is a building with 4 floors, the ground floor, and then three upper floor. The ground floor has a laboratory, and in the laboratory we need to keep certain conditions. And I mentioned that because I will show you something later. So in the laboratory floor, we need to keep the indoor condition always at a fixed level, no matter if there is people inside or not. And regarding our equipment, we have an HV system based on water. We have chiller and heat pump. We have 4 air handling units, 1 per floor, and we have a different fan coils. And so in here, I can show you something that we detected in the very beginning. For example, we have a chiller by carrier, and we detected that the chiller was starting and stopping every 5 minutes. And so we saw this, and we called the carrier, the supplier, and we solved this problem. And that happened in the laboratory because it has to be, the condition has to be maintained all the time. We also, as I mentioned, we also detected, we can also detect that the fan coils and the lighting is on when there is nobody in the building, but people have stayed longer and then left everything on. And we also detected, for example, that we could turn off a certain fan coil because the comfort conditions are okay, and we could be saving energy. So, as a conclusion, we propose an energy digital twin suitable for what we call continuous and advanced energy audit. And so because of this continuous energy audit, we are keeping our model very good calibrated all the time. And we have identified since the very beginning advantage regarding the operation of the building. We have identified some bad behavior, some malfunctioning of the equipment. And as I say, the energy models are very accurate, so the estimation and the simulation are very similar to the reality. So we reduce the energy gap. We also reduce the risk in the investment. And also this is a nice visualization tool, and so we also raise end user awareness. And due to that, we also improve the energy behavior of the people. And so next step, we are testing and improving this solution in the Horizon Europe project that I already mentioned, and we are also working on the Ntimos too. And this is all.
Thank you so much, Noemi. Any question?
I saw that you worked on Autodesk platform services, right?
Yeah, category what?
Autodesk Forge as
Yeah.
Okay. And did you create basically the visualization of the sensor data on like the right side of the digital twin model?
Yeah.
All of it?
Yeah.
Okay.
All of this, everything here, we have done this system on top of our SAP, which is our ERP system. And so all of this is done. We have the database from SAP, the HANA database, and we have plugins to call the different Autodesk ports and everything. And we have implemented this visualization that you can see on the right hand side. I think this is done with SAP Fiori.
Okay.
Yeah.
And I mean, do you use the Autodesk environment, or do you use it as kind of engine on a web platform?
I'm not very sure of that because I haven't been developing this, but I think, I mean, we have, I know we connect with Autodesk Forge, and I'm not sure about the tools because there has been an evolution also. We have been Visio before, I mean, we've been working on this for a while.
Okay, but I understand that there is no kind of a platform, it's
No.
all on it.
Yeah, all in here, and we use the different, we call Autodesk, we call we also call Energy Plus. I mean, everything is prepared to allocate. We also call Energy Plus.
So it's combination of tools
Yeah.
that communicate with
Yeah.
each other.
Yeah.
Okay.
Yeah.
Okay, very interesting. And congratulations also for the level 4 because it's not easy to
It's not easy.
level 4.
Yeah. Yeah, in this case, because we have done, I mean, we've been working on other collaborative projects where everything is slower because you don't have the control of everything. But here it is our building. This is very, very relevant for our company, and so we have put a lot of effort and we have learned a lot.
Basically, the communication between all the tools in terms of visualization happens in this right side part, or there are also other interfaces which are separated from the Forge environment?
I'm not sure. I mean, I'm not sure because I haven't been developing it. It's a pity because it should be, well, it should be my colleague Gloria presenting this, but she was in another meeting, and so I'm doing it. In any case, she's the energy expert, and we have a team of ICT developers, but she knows everything about the ICT, so I mean...
Okay, but it is clear.
Yeah.
In any case.
Okay.
Congratulations.
Okay, thank you.
Thank you for the presentation. I was hoping to characterize the energy saving that integration has been able to spot so far as operational problem.
Yeah, so we've been doing we have evaluated the energy savings that we are getting. And I mentioned about the level 4 because we have done a small prototype to have our system in our building now, closing the loop and now working, and we are testing it these days. And the solution and the information that we give to our CEO is what we say, and also to our customer. Now we are, in addition to these 2 projects that I mentioned, we are implementing this for other customers, so in particular to, in an office building, in a big office building in Malaga, in a company called Mayoral, and in there, the people in there were happy because the question was how much energy I'm going to be saving. If I'm going to be saving energy, then this is worth it, otherwise, don't bother me.
Thanks so much. We have many questions, but later in the lunch we'll talk about it. So Dimitrios, your turn. No? Is it the next presentation? Okay. I'm confusing all the people, so. Nice to meet you.
So, hi everyone, my name is Dimitrios Ntimos. I represent IS, and I'm here to present you, thank you, a new European funded project called TwinAIR. And it's not a paper presentation, it's rather than introducing you to the concept of this project TwinAIR, which is about health in indoor environment. mostly. And we responded to the call of environmental and health, living and working in a health promoting environment. Today I'll introduce you to the problem that we responded to and our ambition, the consortium, who we are, our methodological and our technological approach. First of all, the problem statement. As you already know, we're exposed to poor air quality, which is a leading risk factor in the global burden of disease study. Ambient air pollution is causing almost 4.1 million premature deaths globally, so it's quite significant. The exposure to the microbiology of a built environment may cause or contribute to significant negative, far-reaching effects on human health, including infectious and respiratory diseases, allergies, and even cancer. And I believe in the pandemic, we all saw how important is the air that we breathe inside the building. Now, household air pollution. So, from solid fuels causes 2.3 million deaths each year and combined over 200 million disability-adjusted life years globally each year. You may already know the main indoor air pollutants like very small particles, PM 10, PM 2.5, ozone, carbon monoxide, and other like compounds, like volatile organic compounds, radon, toxic metals, all of this stuff we breathe every day in different concentrations inside buildings. So there is a study that says that if we improve indoor air quality, the productivity in an office can be improved by 8 to 11%. And these like DALYs are 2.2 million are lost every year in the EU, and 110 million citizens currently live in buildings with high concentration of these hazardous pollutants. And this is because mostly of inadequate level of ventilation. And of course, it's a combination of the outdoor air, the indoor air. So we'll see how we try to tackle this. And this caused like a discussion at the EU level and brought this initiative, Ambient Air Quality Directives, to include new indicators in air quality. So our response and solution to that is that we want to introduce a technological solution to improve air quality in a wide spectrum of indoor environments, and in parallel we will investigate how these pollutants affect the health of people and try to support the public health, community awareness and policy making. So I'll just skip this one and go show you a little bit of who we are. Like we're 23 partners across 9 countries in Europe. It's like a combination of private and public institutions. So we will pilot basically we will study some pilots where we do research and also deploy some solutions on, and this has to do with vehicles. So we're going to do digital twins of vehicles, and these are intercity bus in Sweden and an autonomous campus bus again in Sweden, and Avanza intercity bus in Valencia that does the route Valencia Madrid, I think, and also their bus stop is one of our case studies here in Madrid. Apart from vehicle digital twins, building digital twins of Bristol University campus, an office of in Valencia, Linköping student house, a hospital in Greece, schools in Dublin, offices in Germany. So it's a broad range of case studies. So now looking at the solution with a three-pronged methodology: environmental, health, and technical approach. And again, since we're talking about digital twins, we need to measure what's happening in the buses, in the various rooms of all these case studies. We take the data, we connect it to our digital twin, analyze it, provide services and feedback, trying to improve the indoor air quality, and also studying the correlation of indoor and outdoor pollution. So the environmental approach, the first tier is identification and characterization of pollutants and indoor and outdoor correlation. So that's a scientific study. The health approach, which is again a scientific study, is about innovative air monitoring methods, evaluating the particles affecting health, continuous health measurements and questionnaires to track the well-being and respiratory symptoms, human microbiome studies to examine the effects of the air composition of the human body, and health impact assessment according to the EU guidelines. And finally, the digital twins, the technology, multi-level digital twin representing indoor air quality. So this is a digital twin for air quality. Collect also for the built environment and the transport. Of course, open source, interoperable and secure data management will be included. Data analytics services, including physics-based and AI-based simulations. And we're leveraging IoT, virtual sensors, HVAC systems, wearable devices, and external sources of data to create those digital twin models. So now the technological approach and all the studies going to be divided in 8 interventions. So the first one is the digital indoor air quality characterizations, creating a library of contaminants, digitalizing the particle pathways and the heat, the air transfer mechanisms inside the buildings. And this way we will bring more intelligence to our current building digital twin that we have with the air transfers and the indoor air quality study. The vehicle digital twin, quite interesting, not my field. I saw it and I said, okay, that's quite interesting one. So we will place sensors into the buses and trying to analyze, to predict the passengers' comfort, the exposure of the passengers to pollutants, and this includes not only one location, but the whole route that the bus follows. And this means that we need to create microclimates using existing weather files to study this. Quite interesting. Human digital twin, using wearables like smartwatch. Wearable that will capture the air quality. That we will facilitate dose response experiments. So we will expose some kind of experiments to expose into those, to get insights from the health approach. And we'll create an aggregator for a wide range of data sources and profiles. The fourth intervention is about the building asset operation and control for improved indoor air quality and energy efficiency. So we combine here better control of the ventilation in the building to promote both energy efficiency and improving the air quality. Maintenance and optimization, algorithms that prioritize maintenance mainly. TwinAIR real-time indoor air quality rating and awareness. So we will create like a real-time air quality index calculator based on the European Environmental Agency air quality index. This is this air quality index is mainly on the outdoor air. So if you might notice in like some weather apps, they're starting including this air quality index into their user interface. So something similar we'll do, but for indoor spaces. We'll mainly study those 5 key pollutants and investigate if modification to the existing air quality index are required. Social engagement, we will interact with stakeholders, provide the tools, collect their insights, and finally, the building air quality digital twin, as I mentioned before, that will include decision-making, application leveraging physics-based performance digital twin. It will enable users to test various operational renovation scenarios to ensure optimum air quality and energy efficiency, and facilitating for other intervention and services. So this is a screenshot of our own physics-based engine that we can collect the data, create the model, and there is a plugin already that is doing the air transfer analysis. And this tool we're gonna try to make it more accessible through the cloud, like making it working in the cloud with communication exchange protocols. And that's it for now. We're a new project started in October, and as far as I know, all the deliverables will be public. So this means that if you follow us on social, you will be able to download for free and on time all our deliverables.
Thank you so much. So any question?
Right on time.
Yes, I was interested in part of the vehicle digital twin, but I think you kind of explained it because you said that it's more related to the comfort of the passengers. No?
Exactly. Yeah.
But don't you plan kind of to do?
So it's basically air quality digital twin. Yeah.
Okay. So you would have, like for the buildings, the 3D model or BIM model. I don't know if it's called BIM model for a bus.
To be honest, we are still in meetings, negotiation, how we're gonna do it. So it's a very fresh thing. But as far it's like a room that moves, you know, not a static thing. So a lot of things change. Like we need to track the location, the climate conditions inside and outside the bus, inside the bus stop, outside of the, like the terminal.
Anyway, it will not be the digital twin of, let's say, the performance or the consumption of the bus.
I think no.
Okay.
That's out of
The
scope.
dynamic or something.
But the terminal here in Madrid is a quite interesting one because the bus enters the terminal, and I imagine there the air quality is worse than outside. So it's gonna produce some useful results, in my opinion. Yeah.
Okay.
Regarding the mobility, I was wondering more related to the manufacturers, the trains, bus manufacturers, to incorporate this kind of tools into their HVAC systems, and maybe could be one.
Yeah, it would be interesting, like the using like a wireless IoT on public transport. Yeah, and even inside the bus, outside of the bus, like to have sensors. And yeah, and also I really like the keynote presentation of Esther. She was talking about the health of our cities, not only energy savings, comfort, but the health. Okay, so that's our main topic, to improve the health of living in the cities, people living in the cities.
Thanks so much. Any other questions? Yeah, more. Do you have a specific date for a proposed release incorporating these air quality tools into virtual environment or eye scan products? Or
So I think now this year we're delivering a first prototype that we will need to test. But again, it's quite early in the project to be able to show something to you today, but maybe in the next edition of Sustainable Places, I'll sign up to show you some more. Yeah.
Okay. Because I was thinking of the deployers and also the manufacturers of the air quality systems. And in Madrid, there are a couple of them, and we would be really interested in a nice scan incorporating the sensor, outputs, all this kind of information.
Yeah.
Okay.
Hopefully.
Thank you. Thanks so much. Really good.
Thank you.
So thank you so much for this session. So you can just feel free to go.